First simple machine that we're going to be discussing is a lever. A lever is just very simply a bar that pivots around a fulcrum. And so if I have a drawing of a lever here, here's my bar. You can actually think of a teeter-totter for this first example. And the fulcrum is the thing that it's sitting on, the thing where it's going to pivot back and forth like this. So you always have a part of a lever that isn't actually moving, it's staying in the same spot. So here, the middle of the teeter-totter isn't changing its position, it's always staying exactly in the same spot. And the pivot point is right here in the middle, okay? So with a lever, you're also going to have the effort, the end that you're pushing on, or the resistance, the piece that you're trying to move. Now levers, you're not always going to push on them. Once in a while you may be trying to pull on them, but this is where you're going to apply the force, the effort, and the resistance is where you're trying to actually get the job done, okay? Now when we calculate mechanical advantage, and remember what I told you before, we're always going to be calculating ideal mechanical advantage. We're not going to worry about the actual mechanical advantage. So if you see me write MA, it's the same thing as IMA. We're talking about the ideal mechanical advantage of a lever. So the way I calculate that is I'm going to take the distance from the fulcrum to the effort, and I'm going to divide that by the distance from the fulcrum to the resistance. Now I'm going to do some examples here to show you what I mean with several different situations where I'm going to apply this particular kind of lever with the teeter-totter. Okay, so let's say that we start out with a teeter-totter and I have two kids that are of equal weight and they're teeter-tottering back and forth. If that is the case, then the teeter-totter can be balanced right in the middle, and there can be like a meter on each side if the kids are the same size. So if I want to calculate the mechanical advantage of this particular lever, the distance from the fulcrum to the effort is 1 meter, and the distance from the fulcrum to the resistance is also 1 meter. So if I take 1 meter and divide it by 1 meter, I'm going to get a mechanical advantage of 1. Now notice that there are no units on a mechanical advantage because the meters are going to cancel out, and then 1 divided by 1 is 1. Now if you have a mechanical advantage of 1, what that means is that you've not multiplied force or distance, either one. All you've done is change the direction. So this kid goes down, this kid goes up. This kid goes down, this kid goes up, okay? But neither one has to apply any more force than the other one did because each child is the same weight. So in this particular situation, when your mechanical advantage is 1, all you've done is to change the direction of the force. You haven't magnified the force, you haven't magnified the direction, you've only changed the direction of the force, okay? Now, let's say that you have a situation where you have a heavy child and a light child. And so in that situation, let's say that your light child is sitting on this end and your heavy child is sitting on this end. And so in that particular case, if you have the fulcrum right in the middle, they're not going to be able to teeter-totter because this kid is going to weigh it down and this one won't be able to lift the other one up. By shifting the fulcrum, what you're able to do then is that the lighter child is able to teeter-totter with the heavier one. And so the teeter-totter will work, but you've got to shift the fulcrum. So what does that do to the mechanical advantage? So the mechanical advantage here, the distance from the fulcrum to the effort is 2 meters. The distance from the fulcrum to the resistance in this example is 1 meter. So the mechanical advantage here is going to be 2. So what does that mean? Well, if your mechanical advantage is bigger than 1, what it means is that you are multiplying the force that you're using. Okay, so remember, this is the little kid on this side. I should probably write that over here. This is the little kid, and this is the big kid over here. So I'm multiplying his force, but it's going to cost me because this kid doesn't get to go up as high on the teeter-totter as this one does. So I'm multiplying force but he has to have more of the teeter-totter on his end, that he has to exert his force through a greater distance in order for it to work, okay? But more distance is required. And so as a result, this child doesn't get to go up as high because this kid needs the extra distance over here in order to apply his force, okay? So let's look at it from this perspective now. So now I have, maybe I actually have an adult over here, and maybe I have a little kid over here. And so now, again, I've had to shift the fulcrum so that these two will be able to teeter-totter together, okay? But in order for that to work, the adult can't have as much of the teeter-totter on his end. The kid has to have more teeter-totter on his end. So let's check the IMA here, or I'm sorry, just the mechanical advantage here. So again, distance from the fulcrum to the effort here is 1 meter. Distance from the fulcrum to the resistance is 2 meters. So if I divide that out, now I have 0.5. So if my mechanical advantage is less than 1, the kid gets to travel way more distance than the adult does, but the adult has to use more force in order to allow him to go higher. Okay, so I get a greater distance achieved, but more force is required. Okay, so you can use your knowledge of how teeter-totters work in order to kind of keep all of these different types of scenarios in mind with your mechanical advantage. And no matter what type of simple machine we talk about, these things are going to be true about mechanical advantage. If your mechanical advantage is 1, all you're going to be doing is changing the direction of the force. If the mechanical advantage is bigger than 1, you can multiply the force, but you have to have more distance through that force, through which that force is going to act. If your mechanical advantage is less than 1, you can achieve a greater distance, but you're going to have more force put into it, okay? Now, there are several different types of levers depending on where the effort, the fulcrum, and the resistance are placed. This particular type of lever, where you have the effort on one side, the resistance on the other side, and the fulcrum in the middle, is called a first-class lever. And there are several examples of first-class levers. A teeter-totter is one. A scissors is another one. So if you look at my scissors here, a scissors is actually 2 levers put together. But if I just move the one side, where's the fulcrum? Well, where's the pivot point? Well, it's pivoting around this point right here. So this is the fulcrum. The effort is going to be down here on the handle because that's where I'm exerting the force. And the resistance is going to be down on this end. So fulcrum in the middle, effort on one end, resistance on the other end. Pliers is another example of a first-class lever. So examples would be pliers, scissors, a teeter-totter would all be examples of a first-class lever. Okay, let's look at examples of the other 2 classes of lever as well. So we will make some more space here. In a second-class lever, the fulcrum is on one end, and the resistance is going to be in the middle, and the effort is going to be on the other end. Okay, so this is classified as a second-class lever. The example that they give you in the book is one of a wheelbarrow. And so the wheelbarrow, the wheel on one end is your pivot point as you're lifting that wheelbarrow up. The resistance is in the middle because the load in the wheelbarrow is right here. And then the effort is here because that's where you're lifting up on it. Another example of a second-class lever is a stapler. And so again here, the pivot point is down here where it's attached. The resistance is going to be here in the middle, and I tend to push right here because my effort is going to be right there, okay? So I'm going to have a wheelbarrow, a nutcracker, and a stapler, if I get the right color here. So a wheelbarrow is the one that they use there. A nutcracker. If you've ever seen a nutcracker, they look kind of like this. And so your fulcrum is up here and your nut goes here in the middle, like this that you're trying to crack. And so if you squeeze this together, your effort is down here, and then the nut is right here, and it's the resistance, and then your fulcrum is down there. Okay, so those are examples of second class levers. And then a third class lever is one where the fulcrum is still on the end, but here the effort is in the middle and the resistance is on the end. And so this one's called third class. And so what's an example of a third class lever? A shovel is an example of a third class lever, because if I draw a quick picture of a shovel here. Okay, so here's my shovel. The resistance is down here because this is the dirt that you're trying to move. Your hands tend to go right here, so that's where your effort is being placed. And if you pick the shovel up like this in order to move the dirt, then your fulcrum is going to be up here on the end. So examples of a third class lever are going to be a shovel, a tweezers, a tongs would be example of third class levers. Okay, so if I have my tongs here, again, the pivot point is down here. This is two third class levers put together. I'm going to apply the effort in the middle. The resistance is down here on the end because that's what I'm trying to move there. Okay, so those are examples of a third class, first, second, and third class levers. So here, your mechanical advantage can be 1, it can be greater than 1, it can be less than 1. For a third class lever here, your mechanical advantage is always going to be less than 1. We're always going to be multiplying distance, and we're going to be not only multiplying distance, but we're going to have to increase the amount of force that we use to make that happen. But the benefit that we get out of it is a much greater distance, and so that's actually what's multiplied for us. Okay, so here your MA is always, whoops, I had it backwards. Your MA is always going to be less than 1 for a third class lever, and for a second class lever, your mechanical advantage is always going to be greater than 1. You're always going to be multiplying force with this one. So here you are always multiplying force. Here you are always multiplying distance. And here your mechanical advantage can be greater than 1 or less than 1 or equal to 1, like the examples that we've already done. So depending on how you use that first class lever, any of those particular things can be true. Okay, so you will have some practice identifying different classes of levers and calculating some simple mechanical advantages with your levers today.